In this chapter, we'll go over the reactions at the alpha carbon. The alpha carbon is the carbon next to the carbonyl, and the hydrogen on the alpha carbon are called alpha hydrogens. There are different types of alpha hydrogens and they vary in acidity. So the first type is the alpha hydrogen between the two carbonyls, and this one is the most acidic with the lowest pKa. The reason why it's the most acidic because it's conjugate base. If you have a base in there that takes this alpha hydrogen, this is the most acidic alpha hydrogen compared to these two alpha hydrogens here. So when the base takes this acidic hydrogen, you're going to create the negative charge between the two carbonyls. These are two withdrawing groups. So that this is going to stabilize the conjugate base. If your conjugate base is stable, then your acid is going to be acidic. Another case is whenever you have an alpha hydrogen between two carbonyls. One of the carbonyls is a ketone, like this one, and the other one is an ester. Go ahead and get its conjugate base in there. The conjugate base is less stable now because you do have an electron donating group that is giving resonance in there, and that is going to destabilize the conjugate base, making it less stable. So we are expecting the alpha hydrogen of the beta keto ester to be less acidic than the alpha hydrogen of the dicarbonyl. Now, the more esters you have around the carbonyls in there, the less acidic is this alpha hydrogen. So here, this is the case of the diester. Look at the pKa now, it's increasing. So this is the least acidic compared to the three alpha hydrogens. Go ahead and do its conjugate base. You do have resonance from the two sides, and that is going to destabilize the whole conjugate base structure and decrease the acidity of the diester. If we compare these three types of alpha hydrogens with an alpha hydrogen of an aldehyde ketone and an ester, the alpha hydrogen of the ester is going to be the least acidic with a pKa around between 24 25 compared to that of the aldehyde and the ketone. So if we want to compare the alpha hydrogen acidity trend, a diketone is the most acidic compared to a dicarbonyl that has an ester on one side compared to a dicarbonyl that has two esters on both sides compared to an aldehyde, ketone, and an ester. So the alpha hydrogen of the ester is going to be the weakest acid. This means that if there is a base in there, the base is going to prefer always to take the alpha hydrogen between the two carbonyls. Hydrogens are not very strong acids in there. So you would need a very strong base, and always the role of the base is to come and take the alpha hydrogen. So these are the strong bases that we are going to use. Bases, reaction is always solvent dependent, especially whenever you have two types of alpha hydrogens around the carbonyl. So you always need to look at the solvent and see what type of solvent do you have so that you would know which alpha hydrogen the base is going to come and take. So if you have an alpha hydrogen, the base is going to come and take the alpha hydrogen. So we say that the compound is enolizable. So here the compound is enolizable. And if it is enolizable, we're going to go ahead and form the enolate ion. So base always comes and takes the alpha hydrogen. Now you have to choose the most acidic alpha hydrogen. Here in this case, I only have one type of alpha hydrogen. So if you have more than one type of alpha hydrogen, you're going to get more than one enolate. So base is going to come, take the alpha hydrogen, form a lone pair because you are breaking the sigma bond. So you're going to form a lone pair and a negative charge on this carbon, and this is called an enolate ion. This is another example over here. So the base can come and take all of these alpha hydrogens in there because the bases that we are using are very strong bases. And all of these alpha hydrogens, these are weak acidic hydrogens. So for this one, the pKa is 24. It's the alpha hydrogen of the ester, but still the base can come and take it So the compound is still enolizable in this case, and I'm going to form the enolate ion. So the enolate ion that I'm forming in here is going to be less stable than the enolate ion that I formed from the ketone. The reason why, because the alpha hydrogen of the ketone is more acidic than that of the ester. Always takes the most acidic alpha hydrogen. Here I do have two types of alpha hydrogens, an alpha hydrogen of a ketone and an alpha hydrogen between two carbonyls. This one is more acidic, so this is why the base is going to come take this hydrogen, form a lone pair and a negative charge on this carbon in there. This enolate is going to be the most stable compared to the other two because it came from the most acidic alpha hydrogens. We can also have more than one alpha hydrogen. So let's consider these three examples in here. So let's say if we have an aldehyde over here, here you go, we have a ketone, and we have an ester, say an OCH3 in there, and we have on this one a phenyl group. This carbon over here has 3 alpha hydrogens. So this is going to be my alpha carbon. Here I do have two types of alpha carbons. I have an alpha and I have an alpha prime. Each one have their hydrogens. So here I do have a hydrogen, and a hydrogen. And then here I do have two hydrogens. So I have a total here of 5 hydrogens. Here I have a total of 3 hydrogens in there. And here I have no alpha hydrogen. So if you have no alpha hydrogen, this means that the base has no reaction with this type of reactant. And we would say that this reactant is non-enolizable. These two are enolizable. This means that the base can come and take any one of these alpha hydrogens in there because these are acidic alpha hydrogens, and it can create the enolate ion. So carbonyl compounds, they always undergo acid-base reactions, and the acid-base reaction is always at the alpha carbon, depending on how many alpha hydrogens do you have. If you have one alpha hydrogen, then the base is going to come and take that alpha hydrogen. Now, if we have a case of an unsymmetrical ketone, where we have two different alpha hydrogens, and both alpha hydrogens are similar in acidity, then the base can take any one of them. And that is going to be dependent on the solvent condition. So the reaction is going to proceed at the alpha carbon by the formation of the enol and the enolate. This is the mechanism of the reaction. So base normally takes the alpha hydrogen, create the enolate. The enolate undergoes resonance. This is called a resonance stabilized enolate. So it undergoes resonance, and there you're going to end up having a double bond between those two carbons and negative charge on the oxygen. This is going to pick a hydrogen from the solvent. Normally the solvent can be water or any solvent that has a hydrogen, and you're going to make your enol. The process by which you go from the ketone to the enol, this is called tautomerization. The carbonyl structure predominates, meaning that the direction of equilibrium is, in most of the cases, is going to be towards the ketone and not the enol. The enol is going to be the least stable structure in there. And the reason why it's the least stable structure, because you do have two electron-rich species that are next to each other. Normally, we form the enolate whenever we are working with a mechanism that requires a basic conditions. We form the enol whenever we are working with mechanism that follows the acidic conditions. The reason why we care about the enolate and the enol, because normally the reaction doesn't stop here. We can take it a step further, and we can react it with an electrophile. And when we react with the electrophile, we will have a nucleophile-electrophile reaction. So now here we are using the enolate as a nucleophile. Remember earlier when we were talking about the reactions of carbonyls, we used the carbonyl as the electrophile. We reacted with the nucleophile, and the nucleophile attacked the carbon of the carbonyl. Now, here, what we are doing, we are using the enolate as a nucleophile, and that nucleophile is going to attack an electrophile, Ne positive in there. And what you are going to end up doing is simply adding the E to the carbon, to the alpha carbon. This is called the addition of the electrophile to the alpha carbon, whether you are working with a basic medium or with an acidic medium. Now, the process by which you form the enolate and the enol, we said this is called tautomerization. And tautomerization happens in two mediums. It happens in an acidic medium and in a basic medium. So let's start with the acidic medium. So we're doing tautomerization with water in presence of an H plus. Right now, water is our weak base. This is a weak neutral base. And we do have an alpha acidic hydrogen over here. Because water is a very, very weak base, it's not going to come and take that alpha hydrogen right away. The first step, as usual for the acidic conditions, we need to protonate the oxygen. And the reason why we want to protonate the oxygen is going to be the first step in the acidic condition because we want to introduce a positive charge on the carbon of the carbonyl. So over here, what we did, we introduced a positive charge on this carbon. So now this one is more electronegative. It can pull electrons away from the alpha hydrogen and make this alpha hydrogen even more acidic so that that weak base can come and take it. We do have here CH3 on the side. Now, this can undergo resonance. This is a resonance stabilized cation. And the resonance is simply by moving the electrons to the oxygen. You are going to get the second resonance structure here. So I have my plus charge. This is not a plus charge anymore. This is a lone pair. Here you go. Now the positive charge is on this carbon. So now this carbon is more positive in there. This is a cation stabilized, which is ready now for the water to attack. Now my next step over here is the water. So the water, which is the weak base, it's going to come and attack and it's going to take that acidic hydrogen. So the water is going to come, it's going to take that acidic hydrogen, it's going to form a double bond. And I would end up getting my enol in this case. These two are resonance stabilized cations. In basic medium, we're going to go ahead and use clearly a basic medium in presence of water. Water in this case is going to act as a solvent. Okay. So my first step over here, since OH is a strong base, that strong base can come and take that alpha hydrogen. When it does, you're going to make the enolate ion. So we're going to go ahead and draw our enolate ion. Okay, that enolate ion is again resonance stabilized. So in the acidic medium, you get a resonance stabilized cation. In the basic medium, you get a resonance stabilized enolate ion. You can represent the enolate ion either by having a negative charge on the carbon or a negative charge on the oxygen, and both are true representation of the enolate ion. So both of those are resonance stabilized enolate ion. Now the last step is going to be picking a hydrogen from the solvent. So the enolate ion is going to come pick the hydrogen from the water to become the enol. So in both mechanisms in there, I am forming the enol. In the acidic mechanism, I'm going to form the enol. And in the basic mechanism, I'm going to form the enol as well. The method in order to get to the both enols is different depending on the medium that you are working with. So let's say, for example, you are asked to draw the enolate and the enol of this structure. The first thing that you would need to do is look for the alpha hydrogen. So here I do have an alpha hydrogen on this side. On this carbon over here, I have no alpha hydrogen. Okay, so this means that the base is going to come and take this alpha hydrogen in here. We agreed that in order to form the enol, we need a base. And whether we are doing the tautomerization, because the process to go from the ketone to the enol is tautomerization. So whether the tautomerization happens in acidic or basic condition, you need a base in there in order to take that alpha hydrogen. So when the base takes that alpha hydrogen, you're going to create the enolate. And you can represent the enolate like this, or the enolate can undergo resonance in there. So if it undergoes resonance, then also you can represent it as its resonance structure. So it's going to be a double bond, and this is going to be an O negative. Both are representation of the enolate in there. So let's go ahead and circle both of those. And these are the representation of the enolate. Both are resonance stabilized. Now, in order to get the enol, all what you need to do is do a resonance as we did in the mechanism and allow the solvent to add a hydrogen to the negative oxygen to make the enol form. Ketone form, in most of the cases, it predominates. So this is why the direction of equilibrium is going to be towards the ketone, which is more stable compared to that of the enol. This is another example over here. I do have two types of alpha hydrogens. So if I have two alpha hydrogens in here, then in this case, I'm going to create my enolate. When the base comes, takes this alpha hydrogen, you create the enolate on the side, or I can create the enolate on the other side. Now, once you make your enolate, then go ahead and do resonance in there, form a negative charge on the oxygen, and then add a hydrogen to the oxygen. And this is how you get your enol for this ketone. So here I do have two enol forms for this ketone. The more alpha hydrogens around the carbonyl, the more enols you are going to get. And again, in this example, the enols are not stable compared to the ketone. So let's go ahead and draw the enolate and the enol of the following structure. So I have a carbonyl and I have a CH3. Here I do have two different alpha hydrogens. I have an alpha hydrogen here and an alpha hydrogen there. Two different alpha carbons. So let's consider the first alpha hydrogen here. So to draw the enolate, we're going to allow the base to take that alpha hydrogen and create the enolate in there. This is the enolate ion. The enolate is going to undergo resonance, and this is going to form a double bond. It's going to form an O negative charge with a CH3. We said that both of these, we're going to call them enolates in there. So both of these are ions, and because they are ions, we call them enolates. Now the enolate is going to pick a hydrogen from the solvent, and you are going to end up with the enol form. So the enol part is always an OH next to a double bond in there. And the enol is always less stable than that of the ketone. So this process, we said that it's called tautomerization. And what we did over here is that you took that alpha hydrogen and you added it to the oxygen. And then you took this double bond and formed a double bond between the alpha carbon and the carbonyl. And this is how you get the enol. Let's go ahead and consider the second alpha hydrogen of the structure. So the second alpha hydrogen of the structure in there, here you go. This is the carbonyl. We do have two alpha hydrogens in here. We have an alpha hydrogen here and we have an alpha hydrogen in there. The base is going to come and pick only one of these alpha hydrogens. So let's go ahead and write the enol right away. So again, to write the enol right away, this is what we said. Take this hydrogen and add it to the oxygen, and take this double bond and form a new double bond between the alpha carbon and the carbonyl. So now your enol is immediately, this is a carbonyl and this is going to be the OH. So this is how you get the enol from the ketone. So in most of the cases, the keto form predominates. And the reason why it predominates because whatever is forming is less stable than what you started with. This is why the ketone predominates in this case. This one is going to be more stable. And this one is going to exist around 99% compared to 1% or even less for the enol. Now, sometimes the enol form predominates. Let's take an example. If you start with phenol, okay, phenol does have an enol part over here, although all its double bonds are conjugated, and the system is aromatic. Let's say if I want to go ahead and do tautomerization for the phenol. So to do the tautomerization for the phenol, we're going to go backwards because here I am starting with a phenol. I'm not starting with a carbonyl. This is a reversible reaction. So I can start with the enol, go to the ketone, or I can start with the ketone, go to the enol in there. So the process is over here. We're going to trace our steps back. So the hydrogen here was once belonging to the alpha carbon. So we're going to return it to the alpha carbon. And we're going to take this double bond and add it between the carbon and the oxygen. So you are going to end up getting your ketone in this case. So here you go. This is the carbonyl. You didn't do anything to these double bonds. We're just going to go ahead and leave them the same. Now this is the keto form. And if you've noticed over here, this one is non-aromatic. It's the non-aromatic because I do have an sp3 hybrid carbon in there. This is a non-planar, although it's partly conjugated in this region, but the conjugation is gonna stop at this carbon over here because of the sp3 hybridization. So this one is, even though it is a keto form, but it is not stable compared to its enol form. Now our enol is more stable than the ketone. Okay. Another example is when I have a 1,3-dicarbonyl compounds. So if I have 1,3-dicarbonyl compounds, let's take an example over here. So this is a carbonyl and this is a carbonyl in there. I can go by 1, 2, 3 or 1, 2, 3. So when we want to do tautomerization over here, we're going to put the equilibrium arrows at the end. We're going to target the acidic hydrogen. So this is going to be the acidic hydrogen between both carbonyls in there. And with this acidic hydrogen here, we have only one type of acidic hydrogen. This is another type, but if we compare between both, this is going to be way acidic. So the base is going to come and take this alpha hydrogen. Because this one is symmetrical, it really doesn't matter where I'm going to put my double bond of the enol. Both are going to be the same. So this hydrogen, we said, it's going to go to the oxygen, and this double bond is going to move between the carbonyl and the alpha carbon. This enol form is way more stable than the keto form. So my direction of equilibrium is going to be towards this form and a little bit towards the keto form. So this is the keto form and this is the enol form. The reason why it is more stable is because of the hydrogen bonding. It's an intramolecular hydrogen bonding. So you have two things going on. You have an intramolecular hydrogen bonding, and you have conjugation. Don't forget the conjugation in this case. So over here, I do have conjugation. Both are going to make this structure very stable, more to the enol side. So this is why the direction of equilibrium is going to be more to the enol side compared to the keto side. Esters, nitriles, beta carbonyls, these exist as both enolates and enols as well. So we're going to have a base, take the alpha hydrogen, create the enolate in there. The enolate is going to be resonance stabilized. Both of these, we call them enolates. And then when the enolate picks a hydrogen, then we're going to call it an enol form. The enol form here is going to be less stable than that of the ester. If you have a nitrile, it's exactly the same thing in there. I'm considering this hydrogen over here to be an acidic hydrogen. So if it is an acidic hydrogen, then the base is going to come take that acidic hydrogen and make the enolate as well.